This is Tim. Tim runs a puppy storage facility. He only just started, so he has only one puppy and the space to store exactly one puppy in his facility. Oh, look, he just received a new puppy. Because he kind of likes keeping all his puppies in one location, if he wants to store more puppies, he must sell his current facility and buy a new space that's bigger, like that one, just down the street from his current location. To move into the new space, he has to buy the new space and sell the old one. Then, that takes him 1 unit of time to do. Then he has to move each of the puppies from his old space over to the new space, and finally move the new puppy into the new space as well. Each puppy movement takes 1 unit of his time. But what if Tim gets even more puppies? Since Tim is new, he doesn't know how many puppies he's going to need to store over the course of his business. Luckily, Tim thinks of a new algorithm. If there's space in the current facility, he just adds the puppy into the available space. But if there isn't, he's going to buy a new space that's twice the size of the old, and then move all the puppies from his old facility into the new space. Now there's going to be twice as much space, so there's definitely going to be enough space to add a new puppy. So for example, when Tim gets a new, I'm not sure if that's a puppy, I guess, well, let's just call it an honorary puppy, yeah? When he sees that there's no space to store the new honorary puppy, he sells the old facility, and then he buys a new one that's twice the size of the old facility. And then he's going to move each puppy from the old space into the new space, and finally add the new puppy into a space as well. Now, he has extra space, so when he gets a new puppy, he doesn't have to do all of that over again. He can just add a new puppy into the new space. So, great. But we're computer scientists, and let's think about how to analyze how long it takes to add a puppy into Tim's puppy storage facility. Now, there seems to be two situations here. Now, in one case, let's say that there are 3 puppies and he has space to store 4. And when he gets a new puppy and there's space for it, you can just add the puppy into the new spot. Now, that's just going to take 1 unit of time. Notice that it didn't depend on n being the number of puppies in the facility. And so that's constant time. It doesn't depend on n. So another way of saying it is that this operation takes big O of 1 time, or constant time. Now, when the facility is full and there's no space left, and he gets a new puppy, what he has to do first is buy a new facility that's twice the storage of his old one, then move all the puppies into the new facility, and finally move the last puppy into a free spot. Now, buying a facility, that takes 1 unit of time. Moving all the old puppies into the new facility, that takes n units of time because he had n puppies. And then it takes 1 additional unit of time because he had 1 new puppy. So in total, this took 1 plus n plus 1 units of time. Or in big O notation, that's the same thing as saying big O of n, because the little ones there don't really matter. So this is telling us that in the worst case, when there's no spaces left, when he adds a puppy, it's going to take big O of n time to add a new puppy. That sounds like a lot of work for Tim, but when you think about it, that's kind of an unfair way of analyzing Tim's business plan. Tim doesn't really have to buy a new facility and move all those puppies around every single time he gets a new puppy. He only has to do it every time the facility is full. So let's see if a different way of thinking can analyze Tim's business plan more fairly. Amortize, very roughly, means to spread out a big cost over a period of time. In amortized cost analysis for algorithms, it means that instead of just considering the worst possible case for an operation, like adding 1 puppy, we're going to consider an entire sequence of operations. In Tim's plan, it only takes a lot of time whenever Tim's facility is full. But after he puts in all that work and doubles the size of his facilities, he can add a whole lot of puppies very cheaply. We should really take that into account when we're analyzing how much time this procedure takes. Maybe we can spread out the expensive cost to the cheaper add cost that it allows later on. So let's take a look at how many units of time Tim needs starting from the very first puppy. So let's start with a facility that's able to store 1 puppy. There are currently no puppies in the facility. So when he adds a new puppy, all he has to do is move in the new puppy, and he doesn't need to move any old puppies over or buy new space. So in total, that took 1 unit of time. When he adds the next puppy, there are currently 1 puppy in the facility and only 1 space. So the facility is full, which means he has to buy a new facility with double the space, move over the current puppy, and move in the new one. That takes 3 units of time. When he adds the next puppy, there are currently 2 puppies, but only 2 spaces as well, which means that he does need to buy a new facility again, and he needs to move the old 2 puppies into the new space. That takes 2 units of time, and move in the new puppy, which takes 1 unit of time. That's 4 units of time there. When he adds the next puppy, there are currently 3 puppies and 4 spaces, which means that he does not need to buy a new space. He does not need to move puppies around. He only needs to move in the new puppy. That takes 1 unit of time. And we're going to do it again. Add another puppy. There are currently 4 puppies and 4 spaces. Space is full, which means he needs to buy new space. He needs to move over the 4 puppies into the new space and move in the new one. That takes a total of 6 spaces. That's 4 plus 1 plus 1. And the next puppy, there are currently 5 puppies and a space for 8. So he does not need to buy anything. He doesn't need to move anything. He just adds a new puppy into the space. Same thing for the next few operations. 6 puppies in a facility, and space it will hold 8. There's space, and then buy. Just move in the new guy. Same thing again. 7, 8. There's 1 space, so we don't need to buy. Just add 1, and so on and so forth. So let's see. I'm gonna draw some blocks wherever he starts to buy a new facility up until that facility is full, and hopefully we can see some trends here. So he had 1 space available here, and so that's 1 segment. He had to. Then when he had 2 items, he started here and ends here when it got full. When he bought another one that's size 8, he started buying it in this area, and it got full over here. So let's see. Let's count the total amount of time that he spent in each segment. In the first segment, he took 1 unit of time. The second segment, he took 3 units of time. Third segment, he took 5 units of time. The next segment, he took 9 units of time. The number of ads in each segment, the first one had 1 ad, second one had 1 ad. He had 2 ads here. And the third one, he had 4 ads. Okay, well, what's the average time for adding in this adding something in segment? We take the total segment time divided by the number of ads in the segment. So that's 1. That's 3 divided by 1. That's 3. That's 5 divided by 2. That's 2.5. That's 9 divided by 4. That's 2.125. Huh. Well, and that's interesting. It certainly looks like in each segment the average time seems to be less than or equal to 3. And actually, the trend does follow for bigger and bigger segments. And you can prove that this is the case. You'll actually see some more technical proofs of this when you take a more advanced course in computer science. But let's try to see if we can get an intuition for why it doesn't change as the segment size increases. The slow add operation only happens whenever things get full. But it isn't that bad when we consider that its slowness helped to make a whole bunch of things faster later on. For example, when we added the 2 over here, we could spread it out amongst the 2 add operations within this segment. Same thing with the 4. We can spread it out amongst the 4 add operations in this segment, and the 8 in these 8 add operations, and the 16 in these 16 add operations. So regardless of the size of the segment, or regardless of however many we need to add at any given time, whenever we create a new facility, we can spread it out amongst all the new puppies that we can add for that one facility and that segment. All this tells us is that adding the time it takes to add a puppy, on average, doesn't depend on the size of the facility at all. All this tells us is that even though sometimes it can take a whole lot of time to add puppy in the worst case, in the long run, if you average over a sequence of add operations, it takes constant time, or big O of 1, according to amortized cost analysis, to add a new puppy. That's all for this time, and good luck with your puppy storage facility, Tim. Tim, I did have a question for you. What exactly are you going to do with all these puppies? Oh, wow. Yeah, no. Don't, don't do that, Tim. Many thanks to the photographers who made pictures of puppies and honorary puppies available through a Creative Commons license.